Today's problem was find as many tangent lines as you can which are tangent to this circle. I get the impression that a lot of people are still trying to do problems by staring at the problem hard enough that you think that the process is going to like magically pop into your head somehow. But that's not how problem solving works. The whole point of problem solving is you have to interact with the problem. You have to try things. You have to tinker. And so learning problem solving strategies is learning how to tinker so that you'll be able to see new things. Because just staring and thinking and hoping isn't going to help. We started out by observing there's a couple of really obvious lines. So the horizontal lines at y equals 2 and y equals 6. There's two vertical lines as well. But those seem like special cases. In other words, knowing these two lines doesn't show me any patterns that I can use to create other solutions. So if I were solving this problem, before starting to get clever, I would just think like, could I figure out any other lines? So like, horizontal lines seem simple, vertical lines seem simple. What's another line that seems simple? What about a diagonal line? That seems simple. So what happens if I draw a diagonal line like this? Could I find the equation for this line? And sometimes setting yourself a simple but specific goal is all you need to start working on a problem. Because this one, now you're not stuck thinking in general, oh gosh, like what line do I even start with? Or like, could I write some abstract equations and then like math somehow? So try doing a simple goal. If you want to, pause the video, and now that you have this simple goal, see if you can figure out what's the equation of that line. It seems like I know some things about this right away. Like I know that it's got a slope of -1. So that's nice. So it's like negative x plus something. Or if I wanted to choose a different form for the line, we could use mx minus x1 plus y1. So for this particular example, slope is -1, so x minus x1 plus y1. And now all I would need to do is find a point x1, y1 that lies on the line. I'm feeling like maybe this one's going to be easier because the y-intercept is like way up here somewhere. And like how would I even solve for that? Like in order to solve for the b value, I would need to know an xy coordinate to plug in. But the only xy coordinate that I really could possibly find would be this one. But if I found this one, then I could immediately plug it in here and be done anyway. So to me, it seems like it doesn't make any sense to use y equals mx plus b. It's probably more direct to use this other form of the line. So now I have a sub-goal. Could I find those xy coordinates? Well, now I'm remembering some other knowledge from the course. So we know the angle here is 45 degrees because it's sort of like everything's symmetric, right? It's like touching here and its slope is -1. So if I know that the angle is 45 degrees, I know that cosine will tell me this distance and sine will tell me that distance. Or at least that would be true if this was a unit circle, if the radius was 1. Because the radius is 2, I know that that distance should be 2 times cosine 45 degrees. Okay, so cosine 45 degrees is root 2 over 2. So this is like 2 times root 2 over 2, which is just the same thing as root 2. Great. So I know that this distance is root 2. Did that help me find this x coordinate? Oh yeah, I guess it did, because I see that this distance is 3, and then I'm going to add an additional root 2, and that takes me here. And then you could use the same process to find the y coordinate. So if you completed the rest of the process, we've got that the slope was -1, because we chose it to be that to start with. And then we solved for this point that's on the circle. And now we've got an equation. All right, so did finding this one equation help us with any other ones? So stop for a second and think, are there any other lines that you could solve for now that you have this idea? Go ahead and pause the video and really think about it. So what I'm thinking is probably it would be not too hard to solve for the line on the other side, the line that has a slope of -1 that's across the circle here. It seems very possible to me that solving for the line whose slope is 1 that touches right here and touches right there. So you could solve for all the rest of those lines. That seems like it would probably be very similar. And if you want to, you could go ahead and do that. It's also made me think another thought, though. It's made me think, finding a point on the circle was really helpful in this process. And I started by drawing a line whose slope I knew, and then I found the point. Maybe I could do it in the reverse order. Maybe I could find a point on the circle and then figure out the slope based on that. So, there's a bunch of different ways that you could think about doing that. You could have done this in Algebra 2 trig, actually. So, you know where the center is. Let's just find, some random point on the circle. Like, let's choose an angle of 30 degrees. You could definitely find the xy coordinates here because it would be 3 plus 2 times the cosine of 30 and 4 plus 2 times the sine of 30. So I know that I could solve for that. So that would give me this. So like x minus, whatever it was, plus py. So let's call this px py. And I'm not solving for px py right now because I know that I could. So I just want to think out the rest of the strategy because I know I can always come back and solve for those. Okay, so now could I figure out m? Well, let's draw on the actual line. Okay, so here's the line. So one thing we know is that it's perpendicular to this line because that's part of the definition of tangent. So could we find out what that slope was? Well, if it's perpendicular to this slope, maybe I could find out what this slope is. Could I find out what this slope is? It seems like absolutely. You know this point and you know that point, so you could calculate slope based on those 2 points. 30 degrees is actually just a polar way of describing a slope, so that you could work with. And like once I know the slope here, I know that the slope of a perpendicular line is just the negative reciprocal. So if this slope is q, this would be negative 1 over q. So that seems like a strategy that's going to work, and I could now try and solve for it. And like all of that you could have done last year. None of this uses math that's new to you. What about math that we've learned this year? Well, let's think. So we did a bunch of examples of like parametric and vector-based stuff. So you know that the parametric form of an equation is cosine t an equation. The parametric form of a circle is cosine t sine t. Could I turn it into an equation for this circle? So it seems like I've got to multiply by 2 to make it be the right size, and then it seems like I need to shift it over and up. So let's go ahead and shift it over and up. So x is going to be 3 plus 2 cosine t. Y is going to be 4 plus 2 sine t. Okay, so what has this done? Now I can just plug in any t value I want, and it's going to give me xy coordinates for a point on the circle. So now I've figured out a way of finding any point on the circle I want, and then I'll do the same thing. Once I have the coordinates of the point on the perimeter, then I'll figure out what's the slope from the center to here, and then find the perpendicular slope. A very kind of related idea was some people weren't connecting to parametric. In their head, some people were connecting to the vector stuff that we worked on. So here I've got a constant vector that's 3, 4. And then onto that, I'm going to add a scaled vector that traces a circular pattern. Cosine t, sine t. And really, this is just a fancy way of writing that one. Like these 2 things are really the exact same equation. But if this was connecting more in your head, that would have been a totally great way of writing a point on the circle perimeter, and then you can... There's still other great ways to think about this. So some students asked me, could we solve a system of equations to figure out places where a line and a circle intersect, where the line is tangent to the circle? And the answer is yeah, you definitely can. It's algebraically a little bit intense, so I'll just sort of give an indication. But conceptually, this is a really cool way to think about the problem. In the other approaches that we've seen so far, we used a parameterization of the circle as an easy way of finding points on the circle perimeter, and then we solved for what the slope of the tangent line would have to be at those points. Let's do it the other way around. let's choose an arbitrary slope. For example, like this looks like maybe it's a slope of 2. There's a lot of different lines that have a slope of 2. Here's like a whole bunch of them. And they all have different y-intercepts, and they all intersect the circle at different places. You'll notice that some of these lines don't intersect the circle at all. Some of them intersect the circle at 2 places. But the ones that we care about are the lines with slope of 2 that intersect the circle at exactly 1 location, because those are the tangent lines. So the general approach would be something like this. Let's rewrite our form of the line, and let's say y equals 2x plus b. So now you can plug this in up here for y, and you get an equation that looks like this. X minus 3 squared plus 2x plus b minus 4 squared equals 4. Okay, so now we've got an equation that's got x's and it has b's. So in theory, by using algebra, we could isolate x, and we could say x equals something. And then what would be on the other side is an expression that uses b. Or, instead, we could choose to isolate b, and we'd say b equals something, and what would be on the other side is some expression involving x. So again, just focus on conceptually sort of what would it mean if we isolated x or isolated b. So you know in general, if you've isolated a variable, what it means is that you can plug in a value here for the dependent variable and then calculate the value for the independent variable that makes this equation true. So let's think about what would it mean if we solved for b in terms of x. What that means is that we plug in any x value and then we solve for a b value. So what does that tell us here? It tells us that we can choose some arbitrary x value, like here, like x equals 2. And then when we plug in the x value, we'll be solving for b. And remember, b is the y-intercept here. So what b values are we solving for? It would be the b values for the particular lines that intersect the circle at that x value. So here's one of the lines that's got slope 2. Here's the other line that's got slope 2. And both of these lines intersect the circle at the particular x value that we chose to plug in. And so it would let us solve for what are the b values for these 2 particular lines. Okay, is that helpful? Not for this problem. Because for this problem, we really want to know what's the x value where the line is only going to intersect at 1 point. And it doesn't seem like that's an easy thing to figure out here. So instead, let's think about what would it mean if we solved for x in terms of b. What that means is that now we're going to choose any old b value we want on this side. So we just plug in a value for b, and the equation will let us solve for the x values that make this equation true. Okay, so like what does that mean for the context of this problem? Choosing a b value is exactly like choosing a y-intercept, which identifies exactly one line. So if I chose that y-intercept, that uniquely corresponds to this line. If I chose this y-intercept, it uniquely corresponds to this line up here. So just visually, you can see that some b values that I might plug in, like this one, you know in advance that this equation is going to have no solutions. Even, like I don't even have to figure out what the equation is, because I know based on its meaning that if I choose the b value of like 5 or 6 up here, then my line has no intersection at all with the circle. And that's what the x value you're solving for means. It means what are the x values where the line with that b value and the slope you originally chose intersect with the circle. So some b values I choose and there's going to be no solution because there's no intersection. Some b values I choose, like this one, there's going to end up being 2 solutions. And then some b values I choose, there's going to be 1 solution, exactly 1 solution. And those are the b values that correspond to the tangent lines that we're interested in finding. But the problem is I said you choose the b value. So initially this doesn't seem that helpful because it's like, how are you supposed to know what's the b value you plug in that will make your x have exactly 1 solution? So think this out one step more. if I imagine sort of what this looked like if I expanded it, it looks like I'll have x squareds in there. And it seems like that's the highest power of x. So if I was going to expand this, I'm going to end up with an equation that looks like something x squared plus something x plus something equals 0. And b is just a number, remember? And so b is going to appear in the expressions for these coefficients. So you could use the quadratic formula to solve for x, and you'd have like something plus or minus the square root of something involving b divided by something. Okay, why it might seem like I'm skipping the important steps here, but what I'm actually trying to do is I'm trying to focus on the high-level strategy. So it actually doesn't matter right now what the details of the algebra are, because we're trying to think, if we were to do all this algebra and we get to the end, how's it going to be helpful? So it's nice to be able to kind of think your way through the problem first by imagining what's the form of the answer you'll get eventually, even though you don't know the details of the specific numbers. So I know that this is going to give me a quadratic equation, and then I can solve the quadratic equation, and the answer will look something like this. You know that whatever is inside the square root, if the thing inside the square root evaluates to 0, then that means x is going to have exactly one solution, because you'll have something plus or minus 0 divided by something. And so that's just one solution. If the thing under the square root is positive, that means you're going to end up with two solutions for x, because you'll have something plus or minus the square root of a positive number, and the plus or minus is what's giving you your two solutions. So you'll have something plus that number and something minus that number, and that gives you the two x values. And then, of course, if the thing underneath the root is negative, then that means that this has no real solutions, and so x won't have any real solutions. So what does that mean for us? What that means for us is if you were able to expand this out, use the quadratic equation to solve it, you're going to get this expression for b, and then you can ask, look at the algebra under the square root, and you could say, when does that expression exactly equal 0? Because you know that's going to be the situation where your x value has exactly one solution. And you know that that corresponds to the situation where your x value intercepts the circle at exactly one point. And those are the tangent lines. So you see, solving a system of equations still makes sense. It still lets you choose out amongst an infinite number of lines which are the exact two that cross your circle, that are tangent to your circle. But algebraically, this would be a lot more work than those other approaches. But the reason I told it to you is because, there's other problems where this is actually going to be the only way to do it, or the best way to do it. So it's nice to be able to think your way through the meaning of the algebra, even if for this particular problem it might not be the most direct path. Okay, so I'm sure there are even more approaches, and if I sat down, maybe we could come up with some more. But I guess my big takeaway is, first you have to understand the meaning of the algebra you're doing. How does the algebra relate to the problem scenario? Second, you can't just come up with solutions by staring and hoping. You have to actually interact with the problem. And the way that you interact is by trying things out. You say, what if the slope was 2? What would it mean? How could I figure out what I need to figure out? Or you could say, what if I'm trying to find, the point right here on the diagonal? If this was the point, what are the coordinates? What would the slope be? So, you just test out little ideas that you have. And I think a lot of you are really focused on getting to the solution jumping to the solution directly. And real life problems, you usually can't do that. If you can jump to the solution directly, somebody will have written a computer program that does it for you, and you don't need to do it anymore. So, genuine problems require genuine human ingenuity, and that's the thing that I want you to be practicing. Okay, I hope this was helpful. We'll keep doing problems like this, and I hope you'll get better. Enjoy your weekends.